In this video, we're going to look at section 10.4. So you may or may have not noticed on Blackboard, but there was a video already made for this section, but something went wrong with my mic and the audio didn't record. So in order to save paper, what you're going to see as we go through here, I actually already have this note set filled in. So as we move to new sections where things are written in, what I'd like you to do is, instead of watching the video straight through, pause, write down what's written, and then come back and we'll talk about, and I'll do reminders throughout the video. So you've probably noticed that we skipped section 10.3, and we did this just for time's sake. I have posted section 10.3 notes on Blackboard if you're interested. And then also, if you do take the time to look through section 10.3, what I'm going to do is I'm going to put a bonus point question on the final that comes from section 10.3. All right, in section 10.4, we're going to focus on forecasting. This is going to be the regression approach to forecasting. And so the basic idea here is that we're going to use regression models as forecasting models. In other words, we're going to use the regression techniques that you've already seen, and we're going to use those techniques to predict what's going to happen in the future when we have time data. Now, you will see that we are going to be predicting beyond the range of the data that we have, and we've learned in the past that extrapolation is bad. We don't want to extrapolate, but this is one of those cases where we just don't really have the choice. We want to know what's going to happen in the future. We obviously can't have data from the future, so we're going to have to extrapolate. And we just want to be careful that we don't want to go too far into the future, and we recognize that the further we move away from the data that we have, the more likely we are to have errors. And so if the errors that we have, in other words, they come from time series data, they're probably going to be correlated. And we can use what's called a time series autoregressive model. So let's look at an example here. All right, so we've got the quarterly sales of different mountain bikes for a previous year by a bicycle shop in Switzerland, and we've got that presented below. So take a moment, pause the video, write what I've got down here, and then when you come back, we'll talk through it. All right, so let's first look at our data set. So looking at our data set, notice that we have data from 4 different years, and within each year we have the quarter for those years. In this third column, what we have is time t. So we've got 16 different time points here, so we've just labeled them 1 through 16, and then we have the sales at each of those time points. So notice that y is going to be a function of t. If we look here at the plot, we notice, one, that there is a little bit of an overall trend. So overall, things tend to be moving very slightly up and to the right, but we also see that there's a seasonal effect here. Notice that the sales spike for each of the quarter twos and then dip down for each of the quarter ones. All right, so we're going to determine an appropriate time series regression model to analyze this data. And what you're going to see is it looks very similar to the models that you've seen before. So we're going to start out by defining our variables. So the first variable that we're going to need here is time t. That's going to help take care of our secular trend. And then we notice that there is an effect due to the different quarters, so we want to make sure we include that. So what we can do is we can include quarter as a categorical variable. So notice there are 4 different quarters, and if we're going to include this as a categorical variable, we know that anytime a categorical variable takes 4 different values, that we can use 3 different dummy variables to denote it. And so notice here I've got 3 dummy variables, Q1, Q2, and Q3, where Q1 is equal to 1 if we're in quarter 1, Q2 is equal to 1 if we're in quarter 2, and Q3 is equal to 1 if we are in quarter 3. Combining these variables, we can build our model. So notice here we have the expected value of y is equal to, we have our intercept, we have a term for t, which is going to take care of the secular trend, and then we have terms for each of those 3 dummy variables, which is going to take care of the seasonal. So notice this looks very similar to the regression models that you've seen before. It's just now we're using these different pieces to help us model those different types of trends that we might see in a time series. All right, so we're going to continue on with this example. So first of all, I'd like you to pause. The first question asks to determine the prediction equation for this model using Minitab, we're going to look at pages 20 through 22 of the Minitab output, but pause the video and write down the prediction equation, and then we'll look at the output to see where these values come from. Alright, so let's go through and look at our Minitab output. Again, this occurs on pages 20 through 22. Here on the top of page 20, we have how to fit this model in Minitab. And then we've got some plots, and these are going to help us with our residual analysis, so we'll come back to these. On page 21, you'll notice here under the coefficients, we have the different values needed for the prediction equation. Alternatively, if you turn to page 22, we also have our prediction equation right here. All right. So again, next we're going to look at part C. So pause the video and write this down, and then we'll come back to it. So part C says determine the overall fit of the model and perform the complete residual analysis, including the Durbin-Watson test for autocorrelation at the 10% significance level. So the first thing we're going to do is look at the overall fit of the model, and you're going to see that we do this exactly the same way we've done with other regression models that we have looked at. So we could look at R squared, we could look at S, and we could do the overall F test. You'll see in the output, these are pretty much in the exact same place they've been for all of our other models that we have looked at. And in this particular case, we see that we've got a high R squared, a small s, and a significant overall F test. Now, to save space here, I haven't written these out fully, but you do want to be able to interpret all these and write out that test, again, fully, but we've done so many of these at this point, I've just kind of summarized them here at the beginning. Next, we're going to look at the complete residual analysis. So the first thing we want to look at is the expected value of the errors and if they're equal to 0. So to do this, we can look at plot A on page 20. So if we go to that plot, this is the one I've labeled as plot A, we can see that it looks okay. It looks like there might be a little bit of a pattern here and here. We kind of do go down, up, down maybe, but overall it doesn't look awful. So I'm going to say that that one is okay. And again, remember, you can pause the video at any point to write things down. All right, for the second one, we're going to look and see if the errors are normally distributed. To do this, we're going to look at plot B on page 20. So the one that I have labeled on plot B is this one. This is our normal probability plot. It doesn't look terrible. You will notice there's a little bit, it dips down right here and right here. Also, we could look at our histogram here in plot C, and you'll notice there is a slight right skew here. So we do have a slight right skew. Again, I'm not too concerned here. We do have a little bit of evidence against the normality, but it's not a very strong skew, and the QQ plot doesn't look awful, so I'm not too concerned. We're going to look at plot D to look at the constant variance assumption. So plot D is the bottom one. Now what we're doing as we move across time, we're looking at how much variability we have. So as we look here, notice the plots are spread out, points rather are spread out about this much, and as we move across, we do see a little bit of a dip in a variability here, and then it comes back up. So this one just looks okay. I am a little bit worried about that bottom dip here. It looks like we have less variability, but overall, I'm not too terribly concerned. But we can also use plot D to look at whether or not the terms are uncorrelated. And it does appear that there is a slight curvature as we move through time. It dips down and then back up. So what we could do is perform the Durbin-Watson test. And so remember, for the Durbin-Watson test, we have this assumption that the errors are normally distributed. We've said that looks okay. You know, there's no extreme skews there. And if you go through and perform that test, you'll find that you fail to reject. And I'd like you to check that on your own. You don't have to turn it in or anything, but do confirm that's what you would get. Now, to find the test statistic, if you turn to page 21, you'll notice that's where I'm getting the test statistic of 0.2 probably 2.2. So when I say confirm, I just mean look this value up on the table and see that you really would fail to reject in this case. All right, our last piece we have here is we're going to find the prediction interval for the year 2017. So again, pause the video, write this information down, and then when you come back, we'll look at what we've got here. All right, so if we want to make a prediction for the year 2017, if we look at our data set, notice that the first month, or first quarter rather, in 2017 would fall next. So that would occur at data point 17. So if we go to our Minitab output on page 22, you'll notice that here we have set t equal to 17, and then we're going to get a prediction interval. We could also set t equal to 18 or 19 or 20, but remember, the further we go out in time, the less reliable our predictions are going to be. So what we can say here is we predict with 95% confidence that sales of the bike in 2017, and we should say here the first quarter of 2017, will fall between 15.39 and 19.10. All right, we're going to skip ahead to page 23. I'd like you to pause the video for just a moment. I don't want to read this page to you. There's a lot of text here. So I'd like you to take a moment, pause the video, read through this page, and when you come back, I'll talk about some of the highlights here. All right, so the big idea here is when we think about how points are correlated through time, the idea is that as we get further apart in time, things should be less correlated. And what the different orders of the autocorrelation allow us to do is they allow us to say, well, how far apart in time should things be before they are no longer correlated? And what we'll see here later on in the notes is most of the time the first order is enough. We really only see a large correlation between two time points that are right next to one another. And so we're going to focus on this idea of being correlated through time, and as we move further away in time, things are going to be less and less correlated. So we can look at a plot here. Now what each of these plots are doing is along the x-axis, you'll notice that we have m. What m looks at is the distance in time between two time points. And so we could be 2, 4, 6, 8, and 10. And so here, we use this symbol here to determine the sign and the strength of the autocorrelation. Just like regular correlations, it's going to be between -1 and 1. As we go close to 0, that's going to suggest no autocorrelation. In other words, at most between two time points that are within one another are going to be autocorrelated, and past that we're not going to see the autocorrelation. So notice here we've got 0.2 and -0.2. We can see very quickly as m gets further, as the points get spaced further and further apart, the autocorrelation goes to 0. For larger values that are closer to 1 and -1, it takes us a little bit, the spacing gets further and further apart before we start to reach that autocorrelation as 0. So in other words, for all of these, as the distance m increases, we see that the autocorrelation decreases. It gets closer and closer to 0, but the speed at which it gets closer to 0 is denoted by this sign here. We're going to skip section 10.6, and 10.7 we're going to talk just a little bit about how to construct time series models. And so for the general time series models, there are going to be two different components, the deterministic and the residual component. And so you saw this here on the previous page. So we're going to talk a little bit about how to choose the deterministic component. And it ends up that the deterministic component of the model, it's chosen in the exact same way as all the other regression models that we've looked at. We've still got to think about what variables we're including. It's just now these variables are functions of time, or they might be trigonomic functions of time. And so additionally, we want to think about modeling that trend, that cyclical, and that seasonal effect. So just like when we looked at that mountain bike example, we could see, looking at our variables, okay, the T variable, that's going to take care of the secular trend, whereas the Q1, the Q2, and the Q3, they were going to take care of the seasonal portion. So you want to be able to identify those different pieces. So another important type of model is what's called a lagged independent variable model. And so we're going to look at that. So what we're going to do is we're going to look at an example where we've got a single variable, and then what we're going to do is use values of that variable further back in time to predict what's going to happen in the future. So for example, we could be interested in the weight gain of a baby, and suppose we had these measurements at 8 different weeks. Well, what we could do is use week 1 to predict week 2, 2 to predict week 3, etc. And so lagging is the process of shifting the data by a time period or a few time periods. And just like with the moving average method, which we skipped because it was in 10.3, but if you go through and review that, you'll see we need to specify how far we're going to go in the past in terms of lagging. And so usually this tells us the order of the model. So looking at this model here, what we're going to do is our model is going to be a function of what we call lag 1, 2, and 3. And in the next example, you'll see where those lags come from. So consider the data on the monthly price of gas in 2006, which is a component of the Consumer Price Index. What we're going to do is we're going to use the previous gas prices to predict current gas prices. And then we can use Minitab to fit this model, very similar to what we've done in the past. All right, so looking at our data set, notice here that we have data for January through December, and ignore this down here for just a moment. And then what we've got next to it is just a single variable. We've got the gas price for each of these. Now, how lagging works, if we look at gas lag 1, what we're going to do is take all of the time points and shift them. So this time point gets shifted 1 space, this one 1 space, this one 1 space. A lag of 2 shifts 2 spaces. So notice the 2.359 gets shifted to here and then to here. And these shifted values, these end up being our new variable that we are going to use. So this particular model, what it's going to look at is a lag of 1 and a lag of 2. All right. Whenever you fit models like this, Minitab is going to create what's called a partial autocorrelation plot, and it's going to look something like this. Mainly what you're looking for in this plot is you want to locate the horizontal line at 0. Then what Minitab is going to do is it's going to give you different lags along the bottom. You're looking for when the horizontal lines that go away start to get to 0. So notice we've got a long vertical line at 1, a long vertical line at 2, suggesting that we should have a lag at 1 and 2, but then the line gets very small at 3, so we don't need a third lag. On this page, you can see how to fit this model in Minitab and the resulting output. And again, take a moment, pause the video, write this piece down, and then we'll talk about it. All right, so first we have our prediction equation. And so you'll notice if we go and we look at the output, here's where we can find that prediction equation, very similar to other Minitab output that we have seen in the past. And then to get our prediction equation, we already have the prediction equation. Next, to get our prediction for January 2007, notice if we go back and we look at our data set, if we were to create a new row at the bottom of the table, the next value would be January for 2007. So to get our gas lag 1, we're actually shifting this piece right here down. And to get our gas lag 2, we're shifting this piece over to here. So those are going to be our two values. So you'll notice we've substituted in each of those values here and here. So what I'd like you to do for this note set quiz is here is another example that is just like the gas example. And I'd like you to find the prediction equation using Minitab, as well as finding the prediction for January 2007. So you're going to be doing the exact same thing that we just did. Looking at the rest of the notes, I'm going to have you read the rest on your own. There's no more examples, and I don't want to have to read it to you, so I'm going to have you read those pieces on your own. And of course, if you have any questions, please let me know.